Okay. Hello, everyone. This is chapter 2 of the Introduction to Statistical Learning book club. Like the first chapter, it was just a basic overview of what statistical learning is. So in this second chapter, we'll start diving deep into some of the key concepts like some background knowledge that we need to get to understand the other chapters and basically what we'll be doing throughout the book. So I think this chapter, most likely it's maybe the most important chapter. I don't know, because it gives you an overview of. So it starts by looking at the type of problems we have, like supervised and unsupervised learning. It also talks about whether the problem is a classification problem or a regression problem, and then the accuracy of our models, wherein we looked at the mean square errors and the trade-off between the sort of the model accuracy and the interpretability of the model. Like there is no free lunch, sort of. And then it looks at the parametric and non-parametric models and some overfitting stuff. Yeah, so like we mentioned before, so statistical learning is just trying to use some statistical techniques to do some predictions and inference. Basically, that's what we are interested with. So in this chapter, we'll deal with developing an accurate model uh, that can be used to do some predictions and also some inference. Basically, we're interested in this prediction or inference. So some notations. So this will be the input. The inputs, they are also the predictors, the features, the independent variables, and then the y will be the output, the output or the dependent variable. So we assume the relationship between y and x. So x, it's like a vector of parameters. They could take anywhere from 1 to p. Like sort of they could be any variable that we're interested in. So we could model y as this. So y is equals to f of x plus epsilon. So here basically what we are more interested in statistical learning is to sort of estimate f. Yeah, this is basically what we are interested in. How to estimate f. So basically the whole book will revolve around what are some of the statistical learning techniques that we could use to estimate f. So which will sort of map the relationship between x and y. So x is usually y is the response, of course, the output. So x is the input. So think of f as a black box, wherein we just give it x, and then it gives us some prediction or some inference depending on the type of problem we have. It gives us the response. So and epsilon is the error term, which is independent of x, and it has a mean of 0. So later we'll see that epsilon has its variance. It's like we don't know it's the variance of epsilon. So for that reason, we'll always have some error in our estimation of f. So later we'll see that. So f is like a systematic information that x provides about y. So here is a classical example where, let's say, we want to look at the effect of years of education on income, on someone's earnings. So looking at the data points, you could see, of course, these are like stimulated data points, but you could see some kind of a positive relationship. It's some kind of linear, but it's not perfectly linear. So basically, this line that connects this curve is what should be f. Sort of, this is what we want to estimate. So in this case, we could say that is our f that we want to estimate. So the differences between the dots and the curve, it's basically like the variance in our x, or the like, yeah. So the variance is in x. So in essence, statistical learning deals with different approaches to estimate F. So basically that's it. So all that we'll be doing in the subsequent chapters is how to estimate F. So there is no perfect model, and the author stressed that there is no perfect model that will give us the true F. So we can never observe the true F, like we discussed before the starting the meeting. Right? We can never observe the true F, but like different models will be suited for different data, and they will give us an F that is very close to the true F. So why do we want to estimate F? For two main reasons. We want to estimate F for prediction purposes. So predict Y using the inputs from X. So the hat, like the Y hat, is like the estimated Y. We get it from estimating the F hat of X, estimated F of X, where F hat represents the estimate, and Y is the predicted Y. So we want to estimate F so that we could get a predicted Y based on F, based on the predictor F. So in this setting, F is often treated as a black box in this setting, wherein we just give it some input, it gives us an output. But this is not always the case, and we'll see that when we want to do inference, because then when we want to do inference, the different X's would have some connection with Y. So in that case, we cannot just treat F as a black box. We really have to understand what X is doing so that we could make connections and try to connect the patterns. So when we predict Y, we have some error, and this error is further reduced into two components: reducible error and irreducible error. So due to the fact that F hat is not perfect, we don't have a perfect estimator. We don't have a perfect estimate for F since we can't observe it. Then we can reduce this error. Depending, if we use a better model, then you could see that the error in the estimation of F could be reduced. So hence the reducible error. Whilst the other error is due to the epsilon we have seen in this equation. So this epsilon is basically inherent in Y. It's some of the unobserved parameters that might affect Y that we can't measure. We don't have any measure for them. So this, we cannot do anything about this error. We cannot do anything about this error. So this error has to be there. So these are unmeasured variables used for predicting Y. Or it could could also contain some unmeasured variations. So no matter how well our predictor is, we still have some error, which is the irreducible error. So mathematically, we could write this like the expectation between the Y and the predicted Y squared is equals to the expectation of F of X plus the error term minus the estimated F all squared. So which we could further break down to the reducible part, which is the difference between the true F and the estimated F, and the irreducible error, which is the error term inherent in F, which sort of we are not able to observe. So in practice, we always don't know how, sort of, we don't know anything about the variance of epsilon, because we don't observe it, so we can't say anything about epsilon. We don't know the variance. So, and the other reason why we need to estimate F, it's because of inference. We want to make some statistical inference. So in this case, we are interested in understanding the association between Y and the various parameters we have, the various X's. So these questions could be useful in predicting which predictors are most associated with a particular response. Like in this example, like here we have years of education and sort of how it's useful for predicting your income. So we could also have like your in the book he gives that example later, but your seniority. We could also have seniority. We could also have variables like your family background, the education level of your parents, and all these things, because these are all factors that will also your gender. These are all factors that will influence your earning. So in that case, we want to make inference, then just doing some simple prediction will not be helpful because we want to see by how much each of the variables, like let's say gender, influence, income, how experience influence income. So in that case, we'll need to do some statistical inference. And then in that case, we cannot treat F as a black box. We want to understand what F is really doing with the data to come up with some of the predictors, the predictions for why we have to know that. So basically, the most common approach to do this estimation, the most common method is to use the linear models. Of course, we could use non-linear models, but later we will also discuss the issues that we might come across if we want to use non-linear model. So the exact form of the F is required, but we don't know that, we don't observe it. So linear models allows us to sort of make the computation of sort of F very easy because they allow for interpretability, but can lack prediction accuracy. So that's a problem with linear models. Whilst non-linear models could be very accurate, but you might find it difficult to to interpret them. That's one of the problems with non-linear models. So now he continues to up to this point, if someone has any thoughts that they want to share, I think that would be cool. Okay. So how do we estimate F? So first, so let's look at some conventions. So N is the number of observations, which is usually the case. Like last week, the first lesson, the first session we had that. So N is the number of observations. The Xij, the value of the J predictor for the ith observation. So basically, the J's are the predictors or the particular parameter, and I is for a particular observation, or it could be individual, depending on the type of data we're looking at. Whilst yi is the response variable for the ith observation. So the training data is what we observe, what we have at hand, the data we have at hand. That's the training data, or let's say the data used to estimate F. That's the training data. So our goal is to find the F hat such that Y approximates to the F hat of X for any observations X and Y. So basically, we want to find a model, like a statistical model that best approximates Y to X. Yeah. So that's basically the what we want to do. So how do we do this? There are two main methods to use to achieve this, which is using a parametric or a non-parametric method. So a parametric method, it's like a two-step approach where we make assumption about the functional form of F. We assume something about the functional form of F. Let's say we assume it is linear. We assume it is non-linear. So we are making assumptions about the functional form of F. So that's the first step in a parametric method. Then the model has to be selected. So now once we select the model, then we fit the model. So once we select the model, now we need to sort of produce a procedure to fit the model using the training data. So now let's say we need an estimator sort of. once we decide that, okay, this is the functional form for the model. Let's say it's a linear. Then we need an estimator. So the most common one is using the OLS, the ordinary list squares method. So through this approach, we could estimate F. So when we consider a lot of parameters, we could make the model very flexible, but then we have a problem of over parameterization or overfitting the data. So which could lead to a lot of so which could lead to a lot of sort of a lot of a lot of variance variability in our model. Yeah. So basically that's it for the parametric method. So the key takeaway for the parametric method is we are making an assumption about the functional form of F, and then we look at the most suitable estimator to estimate F. So while the non-parametric method, we don't make any assumption about F. We just take F as it is. We don't make sort of any assumption about F. About the functional form of F. We just take it as it is. So instead we seek an estimator of F which gets as close to the data points as possible. So it has the sort of a non-parametric method has the potential to fit a wider range of possible forms of F. But it requires a large number of observations compared to a parametric method. So it seems like most of the exercises or most of the problems we'll be dealing with in this book will be sort of making some assumptions about the functional form of F. Yeah, if someone has any thoughts on this, feel free. So next, it talks about the trade-off between prediction accuracy and model interpretability. So we have seen that parametric models are usually restrictive, and non-parametric models are flexible. So basically, if you the whole idea is if you want a more restrictive model, fine, you could have that, but then yes, then there is a sacrifice because your predictions might not be as accurate as when you sort of have a model that is, let's say, somehow flexible. So restrictive models are usually more interpretable, so they are useful for inference. So these are examples of like linear models. They are highly interpretable. Whilst flexible models could be difficult to interpret due to the high complexity of X, because in flexible models we have this problem of overfitting the model. Yeah, then the chapter went on to talk about supervised and unsupervised learning. So supervised learning, we wish to fit a model that relates inputs to output. So basically, in supervised learning, we are expecting a particular output. So basically, that's it. We are. So yeah, Diana is writing something like it was a bit confused about term flexible in this context. Yeah. So that's it. Yeah. Yeah, you're right. It seems to be a bit counterintuitive. So the model is flexible because it could try to fit in the data points as much as possible. Yeah. So which in a sense it reduces the bias, but then it increases the variance. So that's basically that's the trade-off. So as we try to fit the model as much as we can using flexible models, yeah, we have reduced bias, but then there's a lot of variability. So the opposite is when we use restrictive models, then you see that the variance is low, but then sort of the variance is low, but then we have a high bias because of the inflexibility of the model. Yeah, so you're right. So in unsupervised models, sort of we are not expecting any response. Yeah, so we are not expecting any particular response. So whilst in supervised learning we expect a response. So far I think most of the examples he gives is with supervised learning. So on supervised learning we'll have cases wherein I think some clustering and some other machine learning techniques. But then you have some problems which are in between. Yeah, so you have some learning problems that are in between. There's like semi-supervised learning problems, but this is it's not within the scope of this chapter, of this book, sorry. So knowing the type of learning problems we have, then we have the type of the type of so any problem we have, it could be break down to either a regression problem or a classification problem. So when we decide that, oh, this is a supervised learning problem because we have a response variable, then that problem could further be break down to either whether it's a classification problem or a regression problem. So the easiest way to identify this is usually regression problems are when the response variable is quantitative. Yeah, it's example, it's your, let's say, your age, your height, your income, and stuff like that. So when the response variable is quantitative, then we could easily say, oh, this is this is a regression problem. So we could use some of the well-known techniques to solve the problem. But when the response variable it's categorical, let's say it's your gender, race, and stuff like this, then we might use some classification techniques. Yeah. So most of the methods covered in the book can be applied regardless of so we don't have any problem with the x's, the predictor variables, whether they are quantitative or categorical. It's not a problem. We could always use them. The only thing is when they are categorical, we have to give them proper coding and consistent coding so that we could use them. But for the y, which is the response variable, it is important to know whether it's a quantitative variable or a categorical variable, because that will help us to know whether, okay, we have a regression problem or whether we have a classification problem. Yes. So I'm not sure if this is clear or someone wants to add something. So now we go to the interesting part, which is to see how reliable our predictions are, or the model is. So there is no best method for statistical learning. The method's efficacy can depend on the data set. So basically, one method might work well with a given data set, and it might not work very well in another data set. So there is no model that works regardless. So it has to be conditional on the data set we have. So for a specific data set, how do we select the best statistical learning approach? So one of the best ways to measure the accuracy or to know which model, which statistical learning model to use, given our data, is to look at how well the model does in predicting. Yeah, in sort of the performance of a statistical learning method can be evaluated comparing the prediction of the model, whether they are true or real responses. But since we know that we don't actually in real life, we don't observe the true responses. So this makes this exercise very difficult. So later, I think, I don't know in what chapter, he will discuss how can we actually like, so sort of, I think, cross-validation techniques to try to get some of yeah, no. So the basic challenge is we don't observe the true response. So most commonly used measures are the mean squared error, which is sort of the average of the square difference between the yi, that is the actual y, the true y, and the estimated f at a particular data point. Let's say at xi, it could be x0, x1. Yeah. So a small mean square error means that the predicted value and the true response are very close. So we want the MSE to be as small as possible. So this way we could have a good feeling that, oh, our model is quite accurate. So you want the model to accurately predict the unseen data. So that is the test data. So basically, that's the data that we didn't use when we were training the model. Yeah, it could be that maybe we don't have that data, or it could be we have the data, but we didn't use it when we were training the model. So what we want is our model to accurately predict this unseen data, which we will call the test data in this book. So the model gives us the training data and it predicts that very well, but we are not interested in that. So think in the book he gives an example of the test data and the training data as an example, like in a clinical setting where we have a lot of information about the patients, let's say the demographic, some of their demographic characteristics and some of their like personal characteristics, like the height of the patients, their BMI and blood samples and blood groups and all this other stuff. We have it for the patients in our sample. So so basically that's the trained data. So we want to be able to use that to make predictions about other patients that share like similar characteristics. They might not be exact, but they might share similar characteristics, but they are not part of our study sample. And we want to see that our prediction, like our model, is really accurate in predicting these other patients that are not in our study sample. So those are the patients that we will consider in this context as the test data. But the best model will be the one which produces the lowest test data. So not the lowest training data. We are, as a matter of fact, we don't mind much about the training data, because that's not why we are doing this exercise. So it's not true that the model with the lowest training data will also have the lowest test data. That's not true. So this is just an example. So here we have like you can see the graph. We have the various data points. Like this is the X, just like the input, and these are the responses. And we could see the dots or the circles are the various data points. So the true F is the black curve, which is the true F. So because this is a simulated data, we are able to observe the true F, but in reality, we don't observe the true F. So whilst the orange curve is the orange line is the linear, when we use the linear model, this is how it fits the data. We could see that we could see that, oh, this is not a very perfect fit. And then we have the, yeah, it seems to be we have the blue curve and also the green curve. So the orange curve uses a linear model to fit the data to estimate F sort of, whilst the blue and the orange curve, no, sorry, the blue and the green curves, they use some non-linear techniques like the spline plane. Later, I think in the subsequent chapters, we will discuss that. But they use some spline plane techniques, which are nonlinear techniques to fit the data. So basically, that's the data. And then here we see the mean squared error, the estimated mean squared error. And we see that with more flexibility, so first we the squares, the orange and the blue and the green squares are the calculated MSEs, the mean squared errors from this this fit. So the gray curve is the trained data, the trained MSE, which we are not interested in, but this for the purpose of illustration. So the gray curve is the trained MSE, whilst the red curve is the test MSE. In real life, we don't observe this as well, but since this is an example, so it's fine. So we could see for both cases, we could see that the MSE for the linear case is very high. Yeah, you could see it's very high. So and we prefer a smaller MSE. So we could see that, okay, this model is not very accurate just by looking at this. Whilst we could see this line is the basically that's the variance, the epsilon, the variance in epsilon. That line is the variance in epsilon. Whilst the blue square, we could see it's at the lowest point of the test the test MSE. So this is so from this figure, we could see that the blue curve is the model that best fits this data. Yeah. Whilst the green square, we could see the MSE, it's very high for the like the test data. So it's not the preferred model. So in this context, the blue model will be the preferred model for estimating F. So we could see with more flexibility, we could see the higher the variability in the MSE. Like the MSE is very high when we use a model that is very flexible. That is for the test MSE. While for the training MSE, when the model is very flexible, it is low, because what all this almost all statistical learning techniques do is they try to minimize the mean squared error. So that's why we see that the training MSE it's very low in this context, because basically that's what the models do on their own. They try to minimize the mean squared error. So the fundamental property for any data set and any statistical learning method used, As the first flexibility of the statistical learning method increases, the training MSE decreases monotonically. We could see that. This is a general rule. There is no statistical learning method that is an exception. This is basically the general rule. We could see that the training MSE decreases monotonically. And then the test MSE has like some kind of a U shape. Yeah, some kind of a U shape. So as model flexibility increases, the training MSE will decrease, but the statistical the test MSE may not. It may not necessarily have to decrease, but the training MSE will always decrease. And we said the reason for this is basically all statistical learning methods try to minimize the MSE when they are trying to fit the data. They try to minimize the MSE. So small training MSE, but big test MSE implies having overfit in the data, and we don't want that. So we want a case wherein both the test and the train MSE are low, but we are more interested with the test MSE. So, but regardless of whether the model is overfit or not, we always expect the training MSE, like I mentioned previously, the training MSE to be lower than the test MSE. We always expect this because most statistical learning methods seek to minimize the training MSE. So to estimate the test MSE is very difficult, usually because we don't usually have data. Yeah, so we don't have data for that. So later in the book, we'll discuss approaches to estimate the minimum test MSE. I think he mentioned some cross-validation techniques that we could use to estimate the test MSE. So now, before looking at the trade-off between bias and variance, if someone wants to add anything on this, or any comments or thoughts. So we look at the bias variance trade-off. So the expected test MSE at x0, at let's say at a particular observation, say x0, is the expected value or the expected square difference between the predicted y at that particular observation and the estimated f at that particular observation. So it refers to the average test MSE that we could obtain after repeatedly estimating f using a large number of training sets and test each estimate at a particular observation, in this case, like x0. So the variance of a statistical learning method which produces an estimate for f refers to how the estimate function changes. So basically think of the variance as if, let's say here, we add an extra data point or 2 or 3 data points, how will the curves, how will the model fit change? So basically that's a whole idea about it. The variance, we could think of it like that. If we should add 2 or 3 data points, you notice that the linear model will change, but a little bit. But then let's say the other non-linear models, especially the green curve, because it will then adjust to try to fit that other curve as well. So it will have a lot of change. That's why it has a high variability, a higher variance. So bias refers to the error generated by approximating a simply complicated model. So basically, so biases are usually very common when we are working with like linear models, wherein we just try to simplify the model to just few parameters to estimate. So basically we just try to simplify it, make it very simple, and just have some few parameters to work on, and that's what we are going to estimate for the model, and that's it. So we don't have to worry about trying to fit all the errors in that case. So as we make the model much more simpler, or the parameters to estimate much more less, then we have biases that this will introduce. So a general rule, the more flexible a statistical model, the higher its variance and the lower its bias. Yes. So, and the reverse also holds. So for stricter models, we expect that the variance will be low, but the bias will be high. So for any given observation, let's say x0, the following can be proved. Dory book didn't prove that. So we have that the expected test MSE could be break down into three components. We have the variance of estimating f at let's say x0, and the squared variance, the squared bias, plus the variance of the response, let's say the epsilon, the variance in the original variance we saw when in the first equation. So due to the variance and the squared bias being non-negative, the previous so from this, it's clear that to minimize the expected test error, we require a statistical learning method which achieves a lower variance and a lower bias. But also, we learn from this that the expected test mean square error cannot be zero. It cannot be negative. Sorry, it cannot be negative. So the trade-off, extremely low bias but high variance. Like so, example could be like a linear model. We just choose a linear model to fit our model, to fit our data. Sorry, then we could easily have a very low. No. Yeah. No, extremely low bias, but high variance. For example, draw a line which passes over every node. So this is let's say this is a nonlinear case. So in like we mentioned previously, so in nonlinear case, we expect the variances to be very high and the bias to be low. Whilst for extremely low variance but high bias, for example, just fit a horizontal line across the data, then we have a very low variance but a high bias. So in real life situations, f is usually unknown, so it's not possible to explicitly compute the test MSE bias or variance for statistical learning. So this was what was like when I was reading the chapter, this was what was making it difficult for me. I'm like, okay, we don't observe this, but so what do we do? But I think the explanation that Mark gave at the was quite intuitive. So yeah, so I don't know, Mike, if you don't Mark, if you don't mind, maybe you could still, for the benefit of others that didn't get that explanation part. I think that was helpful for me. Yeah.
Yeah, so I was saying, as far as we can never directly observe the reality, we observe the effects of it. So we observe specific events that are caused by an underlying reality, and from that we can estimate or like make a theory about what the underlying reality is. So that's the function. We never have a way to really 100% know or directly observe what that is. We only know how well it fits the how well it predicts the events.
Yeah. Thanks for that. Yeah. So there are some other techniques that we could use to estimate the test MSE using some cross-validation techniques, but I think later in the book he will discuss that. So this approach that we have explained here about looking for the model accuracy, it's this here it's assuming that we are working with a quantitative data. Like it's assuming that we have a regression problem. So the same thing applies in the case where we have a classification problem, where the response variable it's a categorical variable. So he tries to explain that. So the classification setting. So like let's see how the concept recently discussed change when the prediction is categorical. Sort of how do we deal with the model accuracy when we have a response variable that is categorical? So the most common approach for quantifying the accuracy of a estimate F hat is the training error rate. So like, yeah, the training error rate. The sort of the proportions of mistakes made by applying F to the training data, which is usually obtained by summing all the i's from 1 to n, where I is some kind of an indicator. Yeah, I is some kind of an indicator, and it's 1 when yi when the true y is equals to the estimated y, and 0 otherwise. So the stress error rate is defined as the sort of the average. So where the average is computed by comparing the predicted y I hat with the true response yi. So when the lower the test error rate, the more accurate we'll say our model is. So a good classifier is one of which the test error is small. So in the book, he went on to explain how to compute the training error rate, where he talks about the Bayesian classifier, which uses the concept of conditional probability to classify the sort of the training data to the categories that that we are interested in. And then he also talks about the K nearest neighbor, so which classifies a particular response to the data points that are closest to it. But since this will be discussed in a separate chapter, so I thought it will make sense to discuss it there. If not, it might be superfluous. Yeah, so I don't know if someone has some point or some questions also. Some conceptual questions that because we still have like some time, like 5 minutes or so. Yeah. Thank you. Yeah, any comments or yeah, I think these are some conceptual questions. Yeah. So it's like he's saying for each part from A to D indicate whether you generally expect the performance of a flexible statistical learning method to be better or worse than an inflexible statistical method, and sort of to justify. So cases where we have like the sample size n is extremely large, I know predictors is small. So in this case, what do we think a flexible model is going to do? Yeah, I think a flexible model should do quite good. Well, but what do you guys think?
I think it's possible we could run into overfitting with the flexible model there because there's a lot of data and it probably depends on the situation, but I think there's risk of overfitting with a very large amount of data if your model is too flexible.
Yeah, sure.
Yeah, we would have a high variance or
Yeah. So we have high variance. Yeah, of course the bias will be low. Then we'll have a problem of high variance. So
I don't know though, with the small number of predictors, I guess that does kind of make it. Yeah, maybe it's the predictors that really increase the risk of overfitting. So it's probably the other way, actually, now that I'm thinking about it more. I would say that the small number of predictors, you're less likely to have to worry about that. So the flexible model will probably do well.
yeah. Yeah, given the fact that you have a less number of predictors.
Yeah.
This extends outside of this chapter's content, but is that a case where you might want to do feature engineering and take combinations of the predictors, like a multiplicative of two of the predictors and see if you can create more features that way?
Yeah, that sounds good. That sounds like something that sounds good to me. I would agree with that, that if you have a large amount of data for just a small number of predictors, you should be able to try and do that, like feature engineer and get more features. It should be able to support that.
So and I guess when also the variance of the error terms is extremely high, then I think it's obvious that the flexible method might not be the most appropriate.
Yeah, I agree with that too. I think the flexible method will be too influenced by the high error terms.
So when the case we are in, the number of predictors is extremely large, and the number of observations is small, then possibly like we could have some overfitting issues, something like that.
Yeah.
Yeah, I think this one it's more like explain whether each scenario is a classification or regression problem. Indicate whether we are most interested in inference or prediction. So finally, provide N and P. So we collect a set of data on the top 500 firms in the US. For each firm, we record the profit, the number of employees, the industry, and the CEO salary. We are interested in understanding which factors affect CEO salary. Yes, so this would be so this would be a regression problem, I guess.
Yeah. Yeah.
Mhm.
Yes, I agree.
Yeah, I think it's going to be because CEO salary is is a quantitative variable.
Yeah.
And then of course, the N is going to be 500 firms. And then the P's are going to be the profit, the number of employees, and all that. Okay. I'm not sure. I think this one, maybe let's just look at this, and it's already time. Let's just look at this. So when we are considering launching a new product and wish to know whether it will be a success or failure. Okay, success or failure. We collect data on 20 similar products. So that's the sample size that were previously launched. For each product, we have recorded whether it was a success or a failure. The price, so the parameters we have the price change for the product, the marketing budget, the company. So these are all the parameters, and 10 other variables. So the fact here, I think it's going to be a prediction problem. What do you think?
Yeah. Classification.
Yeah. So classification, of course. Yeah, I'm saying. So it should be a classification problem because the response variable is a failure or success. Yeah. Yeah, I think that's it from me. And unless someone wants to add one or two things, but so next week we discuss the lab. Does anyone wants to volunteer to do the labs or? And don't forget to claim the remaining chapters. That way, if anyone is interested in presenting any of the chapters, you could just fill in the claim the Excel sheet. Yeah, then without any comments, we could just end it here. Let me type in.